Everyone, today we are going to talk about rotational kinetic energy, and we're also going to talk about angular momentum. So, we're going to start with rotational kinetic energy. And the thing that's really important for us to remember is that energy is going to be conserved. So, in this case, when we're talking about rotational kinetic energy, oftentimes you're going to end up seeing an object that's running down a ramp. Okay, so if you have an object that's running down a ramp, no matter what that object is, it's going to start with a potential energy up here. And then at the bottom of the ramp, it's going to end up having a kinetic energy. Okay. Now, whenever you have an object that's rotating, it definitely has rotational kinetic energy. It doesn't always have translational kinetic energy. The translational kinetic energy comes in if the axis is moving. So it's moving from left to right or up and down. But if an object is rotating, it always has kinetic energy. So there's going to be motion rotationally. So if we think about it, when we talk about our translational kinetic energy, and that's what we learned in our last unit, we know our rotational kinetic energy is 1/2 mv squared. So if we go ahead and substitute our rotational values for our translational or our linear values, we substitute I for our m and omega for our v. So we end up getting kinetic energy equals 1/2 I omega squared. And I is your moment of inertia, okay? And your omega is your rotational velocity. So we're going to go ahead and look at some problems dealing with our rotational kinetic energy in just a moment. But first, we're going to take a look at objects that are rolling down a ramp. So imagine we have a hoop right here. We have our solid sphere right here. Okay, this is going to be our disk. Okay, and instead of this object right here, we're going to end up having a box. Okay, we're going to end up having a wood or a solid box right here. Okay, so we have our box sliding, we have a hoop rolling, or we have a disc rolling. Okay, and at the very beginning, all of these start with, and say these all have the same exact mass. So the mass of the hoop is equal to the mass of the disc, and that's equal to the mass of the block. Okay, just so that it makes it easy. So all of them are starting at the same exact height, and so therefore they're all starting with the same potential energy. Okay, they're all starting with mgh. But what ends up happening as our block starts to slide down here, it's going down, and all of that potential energy is translating into our translational or our linear velocity or kinetic energy. Okay, which then ends up giving us a linear velocity. Our hoop that's rolling, well, some of that energy, some of that potential energy is translating into energy that is causing it to rotate. Okay, and so we have to use our kinetic energy, that's our linear kinetic energy or translational kinetic energy, plus 1/2 I omega squared. But we need to look at what our I is. So if we're looking at our hoop, I is equal to mr squared. Then when we're looking at our disk, we have 1/2 mv squared plus 1/2 I omega squared. But our I is 1/2 mr squared. So our I for our disk is going to end up being smaller than our I for our hoop. And it's because basically it's easier to turn our disk because of the distribution of mass than it is to turn our hoop. Okay, we can even throw in a sphere here. So a sphere, our I is going to be equal to 2/5 mr squared. And you could even think about what that is going to give you. But in the end, we end up, because we have our I is mr squared, and our omega, okay, omega is equal to our translational velocity divided by our radius, okay? And this is our translational velocity as well. So we end up having 1/2 mv squared plus 1/2 mr squared v squared over r squared, okay? And we're going to look at a sample problem dealing with this in a little bit. But in the end, we realized that the velocity of the hoop is going to be the smallest. The velocity of the disk is going to be a little bit larger, and that's because the rotational inertia is a little bit less because it's 1/2 mr squared. And then our velocity of our box is actually going to be greater at the very bottom of the ramp because all of our potential energy translates into linear kinetic energy. Okay. And so because of that, it ends up giving it more linear velocity in the end. So let's look at some sample problems. In the very first sample problem, we have a 2 kilogram solid wheel with a radius of 35 centimeters is initially at rest. How much work must be done on the wheel to give it an angular speed of 15 radians per second? So remember in our last unit, we talked about work, okay? And let's see, we have an angular speed of 15 radians per second. We have a 2 kilogram solid wheel. We have a radius of 35 centimeters. It's initially at rest. Remember, that's going to be very important. So our mega initial equals 0. Okay. Now, when we looked at work in our last unit, we looked at the fact that our net work is equal to our change in kinetic energy. Okay. So that's going to be equal to our kinetic energy final minus our kinetic energy initial. And that's going to be 1/2 I omega final squared minus 1/2 I omega initial squared. And because our omega initial squared equals 0, this ends up giving us 0. So our work in this situation is equal to 1/2 I omega squared. Okay, so that's going to give us our equation first. Okay, now when we find our equation, we're going to look at, okay, so how much work is done? So when we're dealing with our wheel, we have that our I is equal to 1/2 mr squared. Okay, and then we have our omega final, and that's squared. So we end up having 1/4 times 2 kilograms, okay, times our radius, which is 0.35 squared, times our 15 radians per second, and that's going to end up being squared. So we end up getting that our work done in this situation is 13.8 joules. Okay, so remember, if you look back at last unit, I really talked to you about how it is very important for you to remember the work energy theorem. And that even goes through to rotational energy. Okay, so it's really important for you to remember that theorem. So let's look at this next question. Our next question is a 30 kilogram block is hung from a string that is wrapped around a 5 kilogram disc. So we have a 3 kilogram block. We have a 5 kilogram disc with a radius of 12 centimeters. As the block is released from rest, it falls and turns the disc about an axis through its center. Assuming no friction, how far has the block fallen when it reaches a speed of 1.8 meters per second? So in this situation, we're dealing with a lot of different things. We're dealing with, in the very beginning, we're dealing with an energy of our system. So we have our mechanical energy initial is equal to our mechanical energy final. So let's walk through what is the energy involved in the system. Okay, first, I'm dealing with our disk, and in this case, we have that disk, because it's going to be solid, it's not a hoop, and so the I, or the moment of inertia, of our disk is 1/2 mr squared. Okay, and we also know that omega is equal to V divided by R. Those are two things that we need to remember, and those are things that I would definitely add to your notes. Okay, and this is specifically for a disk. Okay, so let's look at this system. In the very beginning, we have a potential energy. That's all we have. We have potential energy because nothing's moving, everything's standing still. So we have mass times gravity times height. Now, what ends up happening? Well, as the block falls, part of the energy of the block, the potential energy of the block, is translated into energy to spin the disk. And then part of it is translated into energy to have the box drop. So we end up having 1/2 mv box squared, plus we also have part of that energy is translated into getting that disk to spin. Okay. And so this ends up translating into, I'm going to put this in the side, 1/2 times 1/2 mr squared times v divided by r, and that's squared. Okay. So our r squared ends up canceling, and we end up getting 1/4 mv squared. So we end up getting mgh equals 1/2 mv of the box squared plus 1/4 mv squared. Okay. And so when I go ahead and plug things in, because I'm looking for, it says, assuming no friction, how far has the block fallen? So this is what our question is. So I'm looking for what's my H value. So my H is equal to, well, let's look at this. My masses end up canceling. So it's equal to 1/2 v squared, 1.8 squared, plus 1/4 1.8 squared. All of that divided by g, which is 9.8 meters per second squared. And that's going to end up giving me that my height in this situation, the height the block falls, is 0.303 meters. Okay. Now let's look at another question that's also going to deal with rotational kinetic energy. So the main idea in this lesson is that we're looking at how is rotational kinetic energy related to our total energy of the system. And it's very important that you understand that the total energy or the mechanical energy of the system is conserved. Now, your total energy could change if you have work being done by non-conservative forces, though. So in this question, you have a 0.4 kilogram hoop. So if we are dealing with a hoop here, our hoop, our I is equal to mr squared, is released from rest at a height of 0.78 centimeters, 78 centimeters, which is 0.78 meters, above a tabletop to roll down an incline without slipping. Calculate the hoop's speed when it reaches the tabletop. So we're dealing with a hoop that's going to roll down an incline, okay? And that incline is at 0.78 meters, sorry. Okay, so when we look at that, we know our mechanical energy initial, and we're dealing with without slipping, we're dealing with no friction in this situation, mechanical energy final. So in the very beginning, we have mgh initial is equal to, well, first we have translational energy because we know that it's moving linearly, 1/2 mv squared plus 1/2 I omega squared. Okay, so we know that our omega also is equal to v divided by r. So we end up getting mgh equals 1/2 mv squared plus 1/2 mr squared times v squared divided by r squared. Because remember, our omega is v divided by r. So our r squared ends up canceling, and our masses actually end up canceling. Okay, and we're trying to figure out what our speed is. So we end up getting GH equals 1/2 V squared plus 1/2 V squared. So we end up getting V squared. So our velocity is equal to the square root of G times H in this situation, which is 9.8 times our height, which is 0.78 meters. Okay, and that's going to end up giving us 2.76 meters per second. Okay, so now we've covered rotational kinetic energy. Now we're going to go into rotational momentum. So hopefully you can see that in all of this series of all of these lessons, we've just gone through everything that we covered throughout the entire semester, and we've just applied it to rotational motion. So let's look at translational momentum. Translational momentum is equal to mass times velocity. We also have that our impulse is equal to force times change in time, or our change in momentum is equal to force times change in time. So if we translate that into rotational values, L is our symbol that we use for our rotational momentum, okay? And then we end up having, so L is equal to I times omega, okay? And that's also called our angular momentum, or our angular momentum, okay? And so we also have torque, which is our force, our angular force, or our rotational force. Torque times change in time equals change in rotational momentum, okay? Now, if there is no net external torque acting on a system, then any changes in angular momentum for objects within the system must be caused by torques internal to the system, okay? And then also our angular momentum is conserved. So we know that the angular momentum initial, so the sum of our angular momentum initial is equal to the sum of our angular momentum final. Now this is really important because if you think about it, if you've ever watched figure skating and you watch them spin, and it just pull up a video, okay, and they have their arms out. And when they bring their arms in, they are speeding up. They're increasing their velocity. And the reason they're increasing their velocity, or their angular velocity, is because they're decreasing their radius. So they're bringing in their radius, so they're decreasing. So if we look at this in terms of I omega, what ends up happening is a figure skater in this situation, they are going to be decreasing their I when they bring their arms in. If they're decreasing their I, as I goes down, your omega goes up. So your angular velocity increases. Okay? So let's look at some sample problems. We have a couple of sample problems here. In this case, we have a 1.2 kilogram solid sphere with a radius of 32 centimeters is rotating about an axis through its center. So we have 1.2 kilogram solid sphere, radius is 32 centimeters, is rotating about an axis through its center with an angular speed of 0.8 radians per second. What is the angular momentum of the sphere? Well, we know when we're dealing with a sphere, we have I of a sphere, okay, is equal to 2/5 mr squared. So if we look at that, that's equal to 2/5 times our mass, which is 1.2 kilograms, times our r, 0.32 squared, 0.32 meters. So I end up getting that my moment of inertia is 0.049 kilograms times meter squared. Okay, so angular momentum. So when we're looking at angular momentum is equal to I times omega. So I figure out my I, which I already figured out is 0.049. So 0.049 kilograms times meters squared times our omega. And our omega in this situation is 0.8 radians per second. So that's going to end up giving me that my angular momentum is 0.039 kilograms meters squared per seconds. Okay? What is the torque, or what torque would be required to increase the rotational speed of the sphere to 3.9 radians per second over a time of 5 seconds? Okay, so we want to look at this in terms of, so torque would be like our force. And if we're applying a force over a certain amount of time, I'm going to change my momentum. So in this case, our torque times change in time is equal to our change in angular momentum. So our change in time is equal to our I omega final minus I omega initial divided by our torque. Okay? So in this case, or I'm sorry, so we're actually going to solve for our torque. So we end up getting torque is equal to I omega final minus I omega initial divided by change in time. Okay, so we actually don't need this. Okay, and that's going to end up giving us, so it's going to increase the rotational speed to 3.9 radians per second. So we have 0.049 times 3.9 minus our 0.8 radians per second divided by our change in time, which is 5 seconds. And that's going to end up giving me that my torque is equal to 0.03 newtons times meters. Now remember, that is not equal to joules. So please, 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 please do not answer in terms of joules. It's newtons times meters. So let's look at another question. We have a 0.4 kilogram ball is tied to the end of a 1.7 meter long string, and a man holds the other end of the string. If the man starts swinging the ball in circles over his head, and if he is able to apply a constant torque of 3 newtons times meters during the process, how much time is required? So we're looking for time is required to increase the ball's rotational speed to 70 RPM. Okay, so we know, again, torque times change in time equals change in angular momentum. Okay, and we're looking for change in time. So change in time equals change in angular momentum divided by torque. Okay, well, we need to think about this. It is going, so you have a man holds the other end of the string. If the man starts swinging the ball in circles over his head, and if he is able to apply a constant torque of 3 newtons per meter. So he starts swinging it at 0, basically. So I end up having I omega final minus 0, because we're basically starting from rest, divided by our torque. Okay, well, let's think about this. What is our moment of inertia? Our moment of inertia in this situation, because we have a ball, we're going to end up treating that as if it's a point mass, and that's going to be mr squared, which is going to be 0.4 times 1.7 squared. And that's going to end up giving me 1.156 kilograms times meter squared. Okay, and then we're going to look at what's our omega final. Well, we have 70 revolutions per minute. And revolutions per minute, we're going to do 1 revolution is 2 pi radians. And 1 minute is 60 seconds. Pardon my handwriting there. And that's going to end up canceling minutes, canceling revolutions, and we're going to end up getting 7.33 radians per second. So when I go ahead and plug that in here, I end up getting 1.156 kilograms meters squared times 7.33 radians per second, all divided by our torque, which is 3 newtons times meters. And that's going to end up giving me a value of 2.8 seconds. 2.8 seconds. Okay. And you can even take a look at that and make sure that everything is canceling the way that it needs to, so that you end with 2.8 seconds. Okay. And then our very last question for today, we're just going to look real quick at one example of conservation of angular momentum. So here, like I talked about earlier, we have a figure skater who is spinning around. A figure skater is initially rotating in place with his arms above his head at an angular speed of 3.6 revolutions per second. In this position, the skater's moment of inertia is approximately 1.3 kilograms times meters squared. So that's our I initial. When the skater is rotating in his initial position, how much angular momentum does he possess? So what is our initial angular momentum? Well, that's equal to I omega initial, okay, which is equal to 1.3 kilograms times meter squared, and then times our 3.6 revolutions per second. Okay, and I end up getting 4.68 kilograms times meters squared times revolutions per second. Okay. The next question says the skater then extends his arms and one leg, increasing his rotational inertia by a factor of 5. So I final is 5 times I initial, okay, which is 5 times 1.3, which is 6.5 kilograms times meters squared. It says, what is the new angular speed? Well, I know that my initial angular momentum is equal to my final angular momentum. And I know, and my moment of inertia initial times my moment of inertia, times my angular velocity initial is equal to my moment of inertia final times my angular velocity final. Okay, so I know I initial times omega, and my omega is 3.6, is equal to 5 times I initial, which we could go ahead and plug in values here. We could put 1.3 here, and we could put 6.5 there. That's fine. Times omega final. But what I'm showing you here is that you didn't even really need to. So you end up getting 3.6 equals 5 omega final. Divide both sides by 5, and you get your new angular speed is equal to 0.72 revolutions per second. And you have to ask yourself, does that make sense? Well, what happened? I increased my rotational inertia. If I increase my rotational inertia, I'm going to decrease my angular speed. If I decrease my rotational inertia, I'm going to increase my rotational speed or my angular speed. So hopefully that is helpful for you to get started with some of your guys' problems, practice problems that you have. If not, if you have any questions, feel free to always reach out.